Thank you. Thank you for the introduction and for the opportunity to speak. It's very nice to be back. So yes, I will tell you about SCL. I will first tell you what SCL is and give you a brief introduction. And the goal of the talk is to tell you about a geometric method to prove spectral gap results for SCL. So let me start with the definition. I will actually give you three different definitions. So we start with a group G and an element W in G. And the commutator length of G, of W, is defined to be the infimum of the case at least 0, let's say, such that there exists AIs and BIs, such that I can write W as a product of K commutators. So this is like a word length, but with respect to the infinite set of commutators. And I should say once and for all that by this notation, I just mean commutator. I mean, you can pick another convention if you prefer. And so this is an integer or infinity. So if there is if this set is empty, then by convention this is infinity. And a remark that I would like to make at this point is that this is finite if and only if W is in the commutator subgroup, which is the same thing as saying that W maps to 0 in the abelianization or in the first homology. So you can see this as a way to say you have an element. So if it is not homologically trivial, then nothing happens. If it is homologically trivial, then we want to measure the complexity of it being homologically trivial, in the sense that we want to measure the size of the shortest proof that our element W is homologically trivial. So this thing is in general too difficult to compute, but we're going to introduce a stable version that will make our life better. And so this is the main object of this talk. And this is defined to be the lim_inf as n goes to infinity of 1 over n times the commutator length of W to the n. So why do I call it stable? It's stable in the sense that now we have a multiplicative function. So you can take a power of W and you're just multiplying the SCL. And this is a real number, a non-negative real number or infinity. And the analog of these equivalences are that the SCL of W is finite if and only if some power of W is in the commutator subgroup, which is the same thing as saying that W maps to 0 in homology with rational coefficients. So it's like a rational version of CL in some sense. And that is the object that I want to talk about today. So firstly, let me give you a topological way to think about this. And so the topological interpretation, maybe this is a bit in the shade. So now G will be the fundamental group of some space X, and X does not need to be a KG1 or anything. You can just think a presentation complex. And yes, you can just take it to be a presentation complex. In particular, cell complexes it doesn't need to be very complicated spaces. And W is a class of some loop gamma in X. And I'm completely ignoring base points because everything I'm doing is invariant under conjugacy, so base points don't matter. And now the SCL of W can be written as an infimum. And let me first give you the infimizing set. So I'm looking at maps from surfaces with boundary to X. And so I'll use this notation. So I will write the boundary maps to gamma. So those are called admissible surfaces. I will tell you what this means precisely. So by admissible surface, so by this notation, I mean the data of 3 objects. So sigma is an oriented compact surface. F is a map from sigma to X. And I have a boundary map which goes to a circle such that the following diagram commutes. So I can look at the boundary in sigma, and here I have a map to a circle, and here I have a map to X, and this is my loop. So what this is saying really is I have a map F from sigma to X, and this diagram is telling me that the boundary is wrapping around the loop gamma. So it's just a formal way to say this. And I want to add one more condition. I want to keep track of how many times the boundary is wrapping around the loop. So this, I can look at it homologically. This is the boundary, the image in first homology of the fundamental class of the boundary is some integer times the fundamental class of S1, and I will restrict to n being at least 1. I'm just looking at those surfaces with n at least 1. Okay, so now I've told you, I've told you what class I'm infimizing over. I haven't yet told you what I'm taking the infim of, but I'm looking at maps to X with boundary wrapping around gamma a certain number n of times. And what I want to do is to minimize the complexity. So how do I measure the complexity? I can look at minus the Euler characteristic of sigma, and then I divide by the degree. And I need to divide by twice the degree to recover this definition. And I need to do one more thing, which is to say I want to look at the reduced Euler characteristic. Which just means I'm not asking my surfaces to be connected, so I could do something very stupid, like adding a bunch of spheres and just mapping them to points. And that would make this get arbitrarily small. So to avoid this, I'm just saying I'm measuring the Euler characteristic, but I'm ignoring any components with positive Euler characteristic. So yes, this is a topological interpretation. Just I won't give you a full proof that those are equivalent, but to give you an idea, the intuition for where this comes from is that whenever you have an expression like this, you can draw this topologically as having a map from a genus K surface this is genus K with one boundary component, and the standard generators are A1, B1, AK, BK, and then you get that the boundary loop up to maybe switching some AIs and BIs should map to the product of the commutators. So whenever you have an equality like this, you can find a surface of genus K with one boundary component with boundary mapping to W or to W to the n, if you're looking at the CL of W to the n. So that gives you one direction. And essentially the point is that whenever, for any surface, you can reduce to a surface like this and get the equivalence of the two definitions. Is there any questions so far? I should say that you can feel free to interrupt me at any point. I'm happy to take questions during the talk. So I've promised you 3 definitions, and first let me give you an example. So as an example, let's look at the SCL. Let's take 2 elements A, B in our group, and the simplest thing we might compute is what is the SCL of a commutator. And so I'm going to give you an estimate using both definitions. So the first thing is a computation can show you that the CL of AB to the n is at most the integral part of n over 2 plus 1. So this is, I wouldn't be able to do the computation myself, so I won't try to do it. But you can use some tricks to reduce this nth power of a commutator to a product of about n over 2 commutators. So this tells you that the SCL of AB is at most 1/2. But I personally think from this point of view, it's not very clear. It's a bit surprising, but when you see it topologically, so the SCL of AB is at most minus 1 over 2 times the Euler characteristic of a genus 1 surface with one boundary component and the two generators mapping to A and B. So this gives you the same estimate of 1/2. Okay, so that's the easy example. And then, then I promise you 3 definitions. So the third one will be more functional-analytic in nature. So it's kind of a dual interpretation. So it goes via the notion of quasimorphisms. So a quasimorphism on G is a map phi from G to R, such that we're asking that phi is almost a morphism in the sense that a morphism to R is a map for which this quantity is 0 for any A and B. So instead, we're going to ask that this is uniformly bounded over G. And so this supremum is finite. And we call it the defect of phi and denoted by d phi. And we say also that phi is homogeneous if for all W in G and for all n Z phi of. So phi is homogeneous if when you restrict to cyclic subgroups, you get an actual homomorphism. And the theorem is due to Christophe Bavard from 1991 and says that so SCL of W is equal to the supremum over phi homogeneous quasimorphisms with d phi non-zero of so you can see this as a duality result in the sense that you see quasimorphisms as functions on your group. SCL is, you can think of it as a norm or semi-norm. So there is a way to formalize it, which I don't want to get into now, but you can see SCL as a semi-norm on not exactly on your group, but on the space of one chain on your group. And quasimorphisms are the dual functions, and the defect is a norm on those quasimorphisms, or the semi-norm on those quasimorphisms. So it gives you a dual interpretation of quasimorphisms. And so there are many reasons why you could be interested in studying SCL. There are connections with many fields that I don't have time to talk about now, but I'm happy to talk about it later if you want. But one that I want to single out for today is connection with non-positive curvature in group theory. And this goes via spectral gaps. So let me tell you what I mean by this. So the group G has a spectral gap or a spectral gap for SCL if there exists some epsilon such that for all W in G, the SCL of W is either 0 or at least epsilon. So we think of the set of values that SCL takes in our group as the spectrum of SCL, and this is as a gap in the spectrum between 0 and epsilon. And usually, so I'm going to give you a few examples of groups that have spectral gaps. I'm giving you a very general definition, but usually in all the results I will give, we also have control on which elements have SCL 0. So you should think of this as a lower bound result on SCL, really. It's saying for some elements we have SCL equals 0, and usually that's for very obvious reasons. And for the other elements we have a lower bound on the SCL of this element. So this is really a lower bound result. And these lower bounds come from negative curvature. So a few examples are hyperbolic groups, mapping class groups, three manifold groups. And I'm not citing any names, but I can tell more about those results later if you want. But in all those cases, people have used negative curvature notions to get lower bounds on SCL. And on the other end of the spectrum, so the most I want to say the opposite of negatively curved, which is not non-negatively curved, but I mean the opposite is if G is amenable, then SCL of every element in the of W is 0 for all W is a commutator subgroup. So it's like the dichotomy is if you're amenable, you have no negative curvature at all, you're 0, SCL is 0 everywhere. If you have some kind of hyperbolicity or negative curvature, you get lower bounds for SCL. And it's kind of the philosophy of the work I want to talk about today. And I would like to talk about a specific class of spectral gap results. And the story starts with, yes, there are groups where, so usually if you want to construct groups with exotic values of SCL, you will end up with things that don't have spectral gaps. So variants of Thomson's groups that I don't know exactly which, like you can ask Francesco for the exact construction. But yes, I can't write it on the blackboard now, but yes, there are examples. Any other question?
Does SCL being 0 for a particular element have any meaning in other groups?
I can't think of one now. I don't know. It's, yeah, a priori no, I don't know. Maybe it does, but not in an obvious way. Yeah, and it's not the same kind of spectral gap as spectral gap for property T, just to be 100% clear. Okay, and so the particular spectral gap result I want to mention now is due to Duncan and Howie from the same year as Bavard duality. And it says that if G is a free group, then for non-trivial elements in G, the SCL of W is at least 1/2. So this property, so we say that G has a strong spectral gap. A strong spectral gap when star holds. So, and there are two things that make this spectral gap stronger than the other ones. One is that you have the best control you can hope for on which elements have non-zero SCL, which is all non-trivial elements. And the other is the epsilon you get is the best you can get. So let me just say this. So 1/2 is the largest possible spectral gap. And that's because of this example. We know that every commutator already has SCL at most 1/2. So if you had a spectral gap above 1/2, then all commutators would have SCL 0, and then you can check that SCL actually vanishes. So it's the largest possible spectral gap. Well, I guess, okay, with my definition of spectral gap, then if you have SCL 0, you still have a spectral gap, but I think you know what I mean. And the other remark I want to make is if G has a strong spectral gap, maybe I will just write SSG. And H is a subgroup. Then for every non-trivial element of H, so the SCL. So now when I compute the SCL of W, I have to be a bit careful about what group I'm working in, because so what is always true is that there is an inequality this way, because whenever I have a commutator in H, it's also a commutator in G, but the other way around is not true. But I know this is at least 1/2 by assumption, so now I've proved that H also has a strong spectral gap. So it's a property that passes to subgroups, and therefore it can, in principle, at least give you information on the subgroup structure of your group. And one more property is if, let's say, if G is residually free, then so for W non-trivial, so I can do the same thing. So I have a morphism to a free group, and by the same kind of reasoning, I get then SCL of W is at least 1/2. So as a corollary of the Duncan-Harris theorem. So already we get some corollaries from this, and then so almost 30 years later, there was a generalization due to Hoyer, which is that so right-angled darting groups have a strong spectral gap. So I won't define what right-angled darting groups are. I think most of you know anyway. And if you don't, it doesn't matter for this talk. But one point I can make is that they are known to be very important in topology. And for example, this implies that with this remark, this implies that every spatial group in the sense of Hegel and Weiss has a strong spectral gap. So in principle, for example, you could use this to tell whether a group is spatial. When you have a virtually spatial group, you can tell whether it's spatial or not by looking at, or you have an obstruction to being spatial by looking at SCL. So if you know you have an element with SCL between 0 and 1/2, it can't be spatial. So that's potentially interesting for topology. But I would like to focus on this result for now. And the question is, so how to prove that a group has a strong spectral gap? And the method that Hoyer used was and that is also what gives spectral gaps in hyperbolic groups, mapping class groups, and it can give you in 3 manifold groups. So you could see it from another way too, is to construct, so for every W non-trivial, construct a quasimorphism phi. Oh, I didn't into this notation, so. A quasimorphism phi with control on phi of W and D of phi. And then by the theorem, is there a question? Okay. By the theorem of Bavard, so by Bavard duality, you get a lower bound on the SCL of W. And my contribution is to propose a new method, which goes via the topological interpretation of SCL instead. So it's more geometric. So for W, so the counterintuitive thing about this, a priori it seems more difficult because now we want to give a lower bound on an infimum instead of a supremum. So basically this method is interpret SCL via Bavard duality, and then giving a lower bound on a supremum seems easier because you just need to construct one element in this set. Now we need to prove a lower bound on an infimum, which means for every admissible surface, we need to give a lower bound on chi of sigma, or minus chi of sigma. And we need to have a lower bound that depends on this n. So it should be some constant times the degree. And the way this will work is that we will relate the solar characteristic to some curvature via some version of the Gauss-Bonnet formula. And what I would like to do now is, I'm not sure if I will have time to write a precise statement of my theorem, but I would like to explain a bit more about this method and tell you how it works in the simplest case, which is we prove the Duncan-Harris theorem with this method. Is there any question so far before I move on?
Does strong spectral gap play nicely with the word virtually? Fast subgroups can be built.
Yeah, it's so. I thought about it at some point. I'm not sure it's quite multiplicative under the index. I mean, yeah, it's more complicated because you need to look at chains of elements. So it's not entirely clear to me that you can, for example, tell how deep you need to pass to a finite index subgroup to get to a special subgroup, but at least you get an obstruction to specialness. I have one example, which is if you look at if you look at all the surface groups, I mean orientable or not, there is one that does not have a strong spectral gap, which is this one. Which is called Dick surface, and it's also a torus that you can glue so you glue the boundary to a Möbius strip. And this, if you look at at this loop, so the loop, the generator corresponding to the Möbius strip, then this one has a CL at most 1/4, exactly 1/4 actually. So in particular, this surface cannot be special. I don't know any more examples, probably because I don't know enough about two-manifold topology, but yes, if you have some ideas, I'm happy to talk about them.
Well, that's my question as well. Because that would be finitely coupled by an orientable surface, which is special.
Oh, okay. Yes. Yes. Yeah. 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 Any other question? So yes, now let me tell you a bit more about this method. And basically, what I need to tell you more about is, here I told you curvature. I was a bit vague, and I told you Gauss-Bonnet formula. So I want to make a bit more precise the setup in which we're going to have this Gauss-Bonnet formula. And this is the notion of angle structures. So an angle structure on a two-complex. So by a two-complex, I just mean two-dimensional combinatorial CW complex. So it's just a graph with some cells attached to it along rods. On a two-complex X is the assignment of a real number, so that I denote angle of C, with just any real number to every corner C of X. And by corner, I mean, so again, X is just a graph, the one skeleton. And to this graph, I'm attaching some two cells, which are some polygonal, so they are all polygonals. And this is an immersed path in the graph. The boundary is an immersed path in the graph. And so the corner is just something like this. So I'm just defining an angle here. So it is a very combinatorial and a very basic geometric structure. But the point is, from this, we can define notion of curvature. So yeah. Yes, yeah, that doesn't, yeah, they can be more than 2 pi. Yeah, that doesn't matter. And so the curvature of, so let's start with faces. So by a face, I mean a two-cell. The curvature of a face, so let's say it looks something like this, is, so I create f kappa of f. And so how do we define the curvature? You should think, so this will come from the usual Gauss-Bonnet formula. So for example, in the plane, we know what the sum of angles should be. So we look at the sum of angles. So by this, I mean the sum of all the angles of the two cells. And I compare, I know that in the plane, this should be 2 pi times the degree. So the degree is the number of edges, minus, pi times the degree minus 2. So for a triangle, I recover pi, yes. And now if I'm in the hyperbolic plane, then the sum of angles should be smaller, and I have negative curvature. So that should be with a plus sign. Yeah, and that's the curvature of a face. Or you can think of it as if this cell is on a Riemannian manifold, then the usual Gauss-Bonnet formula will tell me that what I've defined here is just the average curvature of my two cells. And now of a vertex, the degree of f is the number of edges or vertices. So it's just a polygon and yeah. And for a vertex, so let's do first the simplest vertex we can think of, which is, for example, what happens on a surface, and let's call it V, is so kappa of V. And now we expect, for example, in the plane, we expect the sum of angles to be 2 pi. In the hyperbolic plane, we're expecting to see more angles, and in the sphere, we're expecting to see less angles. So we should have something like minus the curvature, minus the sum of angles, sorry, plus 2 pi. But that's not quite right because, for example, if V is on the boundary of my surface, then I'm expecting to see pi as the sum of angles. But maybe things are more complicated. So what we need to add is, need to check if it's plus or minus. It's minus. Minus pi chi of the link of the vertex. And by the link, I mean, so the link of the vertex is, you can think of it as a small sphere around the vertex, or what it is topologically. So I'm just looking at the Euler characteristic, and this is the right correction term. So now I have local notions of curvature for my two complex, and the Gauss-Bonnet formula. So right here the proposition, so combinatorial Gauss-Bonnet. No, yeah, I'm just doing planar things because it's easy on the blackboard, but I'm not assuming X is planar. So I'm just saying you choose any assignment of angles, and I'm defining those curvature. And the main point is this theorem, which says once we have those assignments, we have this relation, Gauss-Bonnet, is that 2 pi times the Euler characteristic of X is equal to the sum of the curvature of the faces plus the sum of the curvature of the vertices. And this is, I'm just writing as a proposition, it is easy to check. It's just elementary combinatorics. But the way I think about this is that we have basically this angle structure is allowing us to estimate the Euler characteristic, which is a global property of our two complex, in a local way. So if we define an intelligent angle structure, we can estimate the curvature locally, and then use these estimates to get a global estimate of the Euler characteristic. So it's just a way to move around the Euler characteristic to obtain estimates more easily. Okay, and now that we have this notion of angle structures, I want to tell you how to prove the Duncan-Harris theorem using this geometric method. So proof of the strong spectral gap for free groups via angle structures. I should say that in the free group case, if you look at the Duncan-Harris paper, it's very close in spirit to what I'm going to write now. So I'm not claiming this is a new proof of the Duncan-Harris theorem, but my contribution is in the right-angled darting groups case. So in some sense, I'm generalizing the Duncan-Harris proof to right-angled darting groups. And okay, so we start with an element in a free group, and to make things easier, I will choose my elements in this form. So I'm going to choose an alternating word. So I have something like this with epsilon I and eta I are just plus and minus 1. So this is called an alternating word. And it will just make things a bit easier to write the proof in this case. And now my space X is, I will just take a bouquet of circles. Yeah, and actually, when I say three groups, I meant F2. And so what do I start with? So yes, that's right. Yeah, thank you. So yes, remember we want to estimate. We want to look at every admissible surface. So we start with F, a map to an admissible surface, and I'm going to start by using some black box and say we can make F transverse. And by transverse, I mean we're going to modify F by homotopy. So we're not changing the Euler characteristic or the degree n. And now it looks like my model of transversality is that it's going to look like some bands that map to edges in X. And you should think that this is a trivial I bundle over the edge A. So by which I mean it's like it's a product. It's just a product. So these are the fibers of the map, and then so these are the preimages of the edges, and the preimages of the vertices are some subsurfaces. So then you get another edge maybe here. And then here you have another boundary component. So etc. So okay, this picture cannot happen because you can't have two red edges in a row because of the form of my word W, but this is the spirit. You have preimages of edges are these trivial I bundles over edges, and preimages of vertices a priori are just some subsurfaces like this. And one thing I can do easily is, so this part maps to a vertex. So if I have some topology like I've done here, I can just remove it because I can always, if I draw the same surface without the topology, it just maps to the same vertex, and I have improved my estimate of SCL. So I can assume it is of this form with disks here. And now what I want to do is to define an angle structure on my surface and to use it to get an estimate of the Euler characteristic. So let me tell you what the angle structure is. So the general form, so in general, locally my surface looks like this. These are the boundary components. And these are the parts mapping to edges. And let me, so maybe this, so maybe I should, so remember our board was of this form. So, okay, the blackboards are not very convenient, but I'm just going to write it again. And my surface is oriented like this. And I know, so remember the definition for admissible surfaces was we have this map to X, and this tells us what the map is. So this part maps to a vertex, this part maps to an edge. And we know the boundary wraps around W. So that means here I see some letter in my word. So let's say we see a to the epsilon I. And then we know that this must be b to the eta I. And here, I see another letter. Okay, I'm not here. I'm using this doesn't mean the direction of the A. It just means what way I'm reading it around. So this is a to the epsilon j, and this is b to the eta j minus 1. And now, so here's my angle structure. So I'm going to, the cellulation I'm using is, so there is an obvious cellulation, which is like this. I'm putting vertices there, and those are the edges. But now I'm just adding one more vertex in the middle of each of those strips. And I'm going to define an angle here that depends on maybe, I'm going to call it theta ji. And theta ji is 2 pi if j is greater than I, and 0 otherwise. So it's a very, very crude angle structure. And those are right angles. And yes, and I didn't say. So here I'm just putting 2 pi minus theta ji. So you can see already the vertices, and these are right angles also. So the vertices here don't carry any curvature because here the angle sum is pi, here it is 2 pi. So I don't have any curvature at the vertices. So the goal will be to estimate the curvature of the faces. And yes, maybe if I have time later, I will draw a picture where I can draw a picture where this 2 pi and 0 makes sense somehow geometrically. But firstly, let me tell you where the estimate of the Euler characteristic comes from. So now we need to estimate, so task, we need to estimate the curvature of the faces. So because kappa of vertices is 0. And let me focus on those faces, and I will actually, I will focus on a simple case. I mean, maybe it looks like it's an oversimplification, but I think the idea of where the lower bound comes from is apparent in that example. So the special case is if my face looks like this, so I'm just keeping here a to the epsilon I, a to the epsilon j, b to the eta I, and this is b to the eta j minus 1. And now my curvatures, my angles, sorry, are like this, and this is theta ji, and this is theta, so this goes ji, so this goes ij minus 1. And when I compute kappa, so let's call this face F, kappa of F is equal to, so I need to, where was the formula? It was here. So I need to look at the sum of the angles. So the sum of the angles is 2 pi plus theta ji plus theta I j minus 1 minus what is the degree? So here the degree is 6. 6 minus 2, so minus 4 pi. So I have the sum of the angles of those two angles plus minus 2 pi. But if you look back at the definition of the thetas, what will happen is that usually, so j is greater than I is equivalent to I is at most j minus 1. So this tells you that one of them will be 2 pi and the other will be 0. So the curvature should be 0. But I have lied a little bit because in this notation, remember that we have this word and we should really think of it as a cyclic word. So this eta of j minus 1, if j equals 1, this should really be eta k. And in this case, this equivalent doesn't work. So if this is true only if j is not 1. And when j equals 1, what happens is that you get theta ji equals theta I j minus 1 equals, I think probably I needed, no, this is fine, I think. They should both be 0. Hopefully I got the conversions right. They should both be 0, and then, so kappa of f is minus 2 pi. So of course, okay, I've only looked at the curvature of those faces. I have totally ignored those bands, and I've reduced to a special case. But the idea is usually no curvature will arise, except whenever j equals 1, we get an extra contribution of minus 2 pi. And how many times does this happen? This happens every time the boundary wraps around our word W. So in total, with many computations missing, in total, we get a contribution of minus 2 pi times n. So the sum, so 2 pi times the Euler characteristic of sigma, which was the same thing as the sum of the curvatures, is at most minus 2 pi times n, which means, so this is the same thing as saying minus chi of sigma over 2n is at least 1/2. And so we have our estimate of SCL by taking the infimum. And okay, so that was a proof or a sketch of the proof for free groups. And yes.
Where does the inequality come from? I feel like everything you've taught us until now is all equalities.
Yeah, but that's in what I didn't tell you. Yeah, there are some parts where I think
It's more complicated.
yeah, when you look at some other faces, you will have inequalities arising. Yeah, I don't want to tell you now. I will probably make a mistake, but we can talk about it later if you want. So that was for free groups, and I think I think it's better to stop here than to try writing a statement of my theorem. So yes, thank you for your attention.
Thank you for the great talk. Are there any questions?
Is there any other reason to have negative angles in an angle structure?
To have negative. I mean, I think, okay, I suppose if you think, so you can get angle structures, for example, as coming from some more sophisticated geometric structure, like Riemannian structure or cat zero structure, something like this. but the way I'm using them here really is to say is as I was saying, a way to locally estimate the Euler characteristic. So I guess I don't know. Maybe it can be that in some cases it's useful to have them. I don't have a concrete example in mind, but. I think maybe in the paper of Liu Chen on the Cavalier conjecture, he might have used some. I mean, it doesn't use exactly this language, but what he does is very similar. And I think if you translate his proof into this language, you will use negative angles.
So stable commutator is a limit of a sequence. You can ask not only what the limit of that sequence is, but how quickly it converges. So it looks in this final inequality like this sequence is essentially constant, right? Doesn't look like you have much in the way of narrative at all. No.
I think when you look at it topologically, you lose most of the information about CL in the process. Because the problem is when you want to prove that the first two definitions of SCL I gave you are equivalent, you're going to, in the process, you're going to take some finite covers and create some error terms in this that you can control, but I think you lose control of CL of the sequence in the process.
So they're hidden in the translation.
Yes.
I mean, the convergence you get is something like the difference between looking at a commutator going from a topological thing is the difference between 2g minus, you're looking something like 2g minus 2 over n versus something like 2g over n. And so the thing that you're sort of, so the convergence should be something like 1 over n.
Are there any cases where it's slower?
I don't know.
I think if there is an extremal surface, then it has to be something like 1 over n. No?
I don't know. I've never thought about it from this point of view.
Yeah, no, technically. The only characteristic definition is better.
My original question was going to be the corresponding thing for the amenable case. I mean, that tells you that any amenable group, the number of commutators you need is sublinear, but presumably different groups, there could be a whole spectrum of what sublinear function it is.
Right, I see.
I think that there are no examples where it's not in amenable groups. No known examples. Yeah.
You mentioned the interpretation of these angles. Can you tell us more about why this assignment?
Yes. Yeah, so I mean, it's more of an a posteriori interpretation than where you find them from. But one way I like to think about them is when you want to construct an admissible surface in a free group, one way you can do it is start by writing your word along a circle, which I'm doing this way, so this is connected there. And let me take the easiest word I can think of, which is a commutator. So now it looks like A, B, A inverse, B inverse. And when you want to construct an admissible surface for SCL, what you need to do is firstly pair up those edges. I mean, okay, it could be a power of these two, but what you need to do is pair up those edges by those kind of strips. So for example, here there's not much choice. I can pair them like this. And then I can pair the other two. And and okay, and this goes around. So again, this is identified. And what I've drawn here for now is a surface with two boundary components. So you can check that this is only one if you just go around. And now I have to glue a disk to, so this boundary component already maps to W. This boundary component just maps to the vertex, the wedge point. So I can just glue a disk onto it. And what I recover is the torus. And now if you look at it from this point of view, the angles there. So what really mattered here was the index. So we are keeping track of where we were in the world. So I'll just write it here. It's like 1, 2, 1, 2. And the angle structure is obtained by, so this disk is the outside disk that we have glued here. And so the vertices carrying the angles there, they appear here. They appear here and also there. And this one too. And now if you write, so probably I will get the conversion wrong, but this should be something like, here you have 1, 2, so this should be theta 1, 2, etc. So it should be maybe also theta 1, 2, I think. Yes, something like this. And the point is, in the definition of the thetas, you're looking at, are you going, is j more greater or smaller than j? So here you're asking, am I going forward or backward in the picture? So it's like saying, if I've taken the right convention, it's like saying, here I'm drawing it in some way, these angles are telling me that I should draw the picture like this. That this is maybe, that those strips, they should be like this. So you have outside an angle of 2 pi and inside an angle of 0. So yes, it's like they come from, on the picture, it's like the top angles are either 2 pi or 0, depending on the convention, and the lower angle are 2 pi or 0. So that's the way I think about them geometrically. I don't know if that's. No, it's not. No, yeah. No, it's more like I don't know, visual way to see it. I mean, I guess the visual explanation I have is you can draw the picture on the blackboard, so you get, that means you have 0 curvature everywhere, except you can't draw this part, which is where the negative curvature comes from. So I can't draw the gluing on the blackboard.